All right, so now we're going to talk about affine connections. And as I've alluded to before, the basic idea behind affine connections is to be able to compare tangent spaces on two different points on a manifold. And usually it's like they're assumed to be somewhat close to each other. And the reason is because there's no canonical way to identify it's like two tangent spaces at different points on a manifold. And you need to introduce an additional structure, and that additional structure is what we call an affine connection. Okay, so what we're going to do now is we're going to look at what happens when you have two tangent spaces for two nearby points, and then see what happens. So let's consider two nearby tangent spaces. Okay, so T cos C and T cos C plus D cos C. Okay, and let's say that I have two tangent vectors. Okay, so let's say x, which I'm going to write as xi e sub I at cos C, which is an element of the tangent space cos C, and then let's call that x tilde, right, which is x tilde I e sub I at this slightly offset point, and this is in the tangent space of a slightly different point. Okay, so so these are two tangent vectors. So this is cos C, and then this is cos C plus D cos C, and this is x tilde, and this is x. So the first observation, which should be readily apparent, is that these basis vectors e sub I are position dependent, right? They depend on the base point. And so the fact that you have two different base points means that even if xi and x tilde I are the same, right, we can't necessarily say that those two tangent vectors are equal in any sort of prescriptive sense. So the basis vectors EI, right, depend on the base point. So even if the components xi and x tilde I are the same, right? We can't really say that the vectors x and x tilde are the same, right? Okay. So, all right, but nevertheless, it's like, you know, we're working, it's like with smooth manifolds, and there's a sense in which there's still a well-defined limit, right? So as this delta cos C goes to 0, right, the point, you know, it's like cos C tilde, for lack of a better term, right, approaches cos C. It's like, and so there's a sense in which, you know, if the coefficients agreed, that these two vectors agreed in some limiting sense. Right, so let's try to make this kind of intuition a little bit more precise, right? Okay. So, and so we want to define, in some sense, a one-to-one correspondence. It's like between nearby tangent spaces so that it's like it agrees. It's like it has this limiting agreement, right? So that's part of the motivation, if you will, for introducing these affine connections, is that it gives you a way of saying that vectors at two different points are equal, and it's like, and the basic idea then is that as you move the the two base points closer and closer together, that agreement or that notion of vectors being equal at two different points agrees with the literal notion that they're the same vector when those two base points coincide, right? So, so how should I say that? So the notion of an affine connection defines some sort of correspondence so some one-to-one correspondence between tangent spaces at nearby with nearby base points, right? That limit to the identity when the two base points coincide. Okay, so that's sort of the intuition. It's like there's the affine connection is going to say that, well, two vectors, and more generally, it's like given any vector in one point, it's like there is a corresponding vector at the other point, which we say is the same vector, so to speak, right? And this one-to-one correspondence, it's like between tangent spaces or between vectors, it's like with different base points, is such that as you take the limit as the two base points, it's like approach each other, then in the limit, it's like you actually have that those two things are literally the same vector on the same tangent space, right? Okay. So let's try to make this idea a little bit more precise. Okay. So the basic idea, if you will, is that we want to construct a mapping between the tangent vectors, or it's like, shall we say, the basis for the tangent spaces at two different points, such that if you put this one-to-one correspondence between the basis elements, right, then the notion of it being the same vector would be that the components are the same, right? So that's kind of a natural construction. All right, so we want to sort of introduce an affine connection as a means of mapping basis vectors from it's like T cos C plus D cos C to T cos C. All right, and then all right. So the map from sort of EI prime in T cos C to E tilde I in T cos C plus D cos C, right, is close to EI cos C. And we do that because at the end of the day, it's like when this d cos c goes to 0, we want this agreement. It's like with the original basis element, right? So we can represent it as so I'm going to represent this as e sub I prime is equal to e sub I plus d ei. Okay. Then I can write this difference in terms of its components, right? So this is ei plus d eij ej. And then it has to have the property that, it's like this goes to 0. It's like as d cos c goes to 0, right? But you want that d eij goes to 0 as d cos c goes to 0. All right? So what can happen is that I can write this term now. It's like as, some linear combination of that infinitesimal d cos c, right? And also want some linearity, okay? Also want this to be linear. This d eij to be linear in d cos c. So I can write d eij as some what is going to be called a connection coefficient, the gamma kij, which depends on the point cos c, and d cos ck. Okay, so it's going to contract over the components. It's like of d cos c, right? And then you just have an ij dependence, which is what we have here. Okay. So when you put that all together, what is that saying is that this new basis element, right, is equal to the old basis element plus gamma kij cos c d cos ck ej. All right, so let's just sort of see. You have a repeated index for j, a repeated index for k. So those two will contract out, and you're just left with dependence in the subscript. It's like to I. It's like, and that's sort of consistent with the other terms, right? So to first order, it's like to the leading order, it's like the sort of the new sort of coordinates. It's like relative to the old one is given by this relationship. So so this is sort of the first order approximation of how the basis changes. Right, as we move the base point. By sort of d cos c, right? All right, so anyway, so this linear correspondence, it's like between tangent spaces at two nearby points, is then uniquely specified to leading order. It's like by this entry here, right? By this, what is called a connection coefficient. Okay, so let's see what happens. So, so this linear correspondence between t cos c and t cos c plus d cos c, right, is established by specifying an affine connection right, gamma, which is expressed in terms of these sort of index quantities, Kij, right, which sort of has 3 indices, right? And as you recall, one of the indices has to do with the fact that it has this dependence. It's like on where you are. It's like, you know, how you've perturbed the point. It's like by this d cos c term. It also has the fact that there's this change of coordinates, right, which is usually represented by a matrix, which is the 2-index object. But that matrix, that linear transformation, again depends on where you are in the nearby point. So that's why you have 3 indices. Okay, all right. So so these sort of 3-index things are the connection coefficients. So the gamma Kij are the connection coefficients. And you can obtain them in the following way. So okay, so let me sort of take a step back. So if you recall, it's like we had written down EI prime as EI plus D EI, all right? So, you know, when you've moved that base point slightly, it's like you get this shift. It's like in the basis element, right? So, so you can express, it turns out it's like these connection coefficients, right, in terms of inner products. It's like between this perturbation, it's like, and the basis vectors. Okay, so the coefficients, the connection coefficients are given by the inner product of DEI and EM as follows. Okay, so DEI, EM, okay, so this is equal to gamma Kij G JM. It's like D cos CK. All right, and then if you recall, it's like when you have the metric in this way, it's like with this repeated index on one of them, this gives you a way of lowering that index down here, right? So this gives me gamma Ki M D cos CK, right, where this is equal to this, right? All right, so more generally, it's like this is, you know, this is the process by which you raise and lower indices is through the metric, right? So if you have something in an upper index form, it's like you want to, you know, bring it down to a lower index, right, you contract it. It's like with a metric tensor in this way, right? Okay. So, all right. So anyway, so this is one formal way of doing this. It doesn't really tell you ahead of time, you know, it isn't a prescription nevertheless, right, for how to specify the affine connection, right? Because all we're saying here is that these connection coefficients are related to this inner product, which in particular depends on how DEI it's like contracts, or it's like pairs with, actually is inner producted, it's like with EM, but this DEI is still something you have to choose, and you want to choose it in a way it's like that it depends, it's like on this D cos C term, right? So, so this still leaves the whole question of how do you specify the affine connection. More generally, it's like open, right? It just says that you can characterize, it's like this identification of tangent spaces of nearby points, right, in terms of these connection coefficients of the affine connection. It doesn't tell you how to choose one, right? So one very common way of choosing an affine connection is the one which is induced via the Riemannian sort of metric, right? So one way to introduce an affine connection right, is to consider the one induced by the Riemannian metric. Okay, so one way to sort of think about this is that if you have an affine connection, the net effect of the choice of the affine connection is to introduce the notion of parallel transport. What that basically means is that if you start with a vector, it's like at a given initial point, and you specify a path which goes through that initial point and then goes nearby, it's like you can sort of construct exactly this one-to-one correspondence between that tangent vector at the base point and you know, tangent vectors along that path, right? So this leads to the notion of parallel transport of a tangent vector along a path with respect to this affine connection. Okay, so you might recall that at some point in time we discussed this idea of connections being compatible in some way. It's like with the Riemannian metric. More in the context of the kind of connections which are induced, if you will, it's like by divergence functions, and the fact that they don't do the usual thing Levi-Civita connections do. It's like, which is that if you parallel transport two vectors via the Levi-Civita connection and you take the inner product, you get the same inner product, right? So anyway, so so we're sort of going back just to the Riemannian case here. And in the Riemannian case, right, one very natural choice of an affine connection is exactly the Levi-Civita connection. And Levi-Civita connection, amongst other things, has the property that when you take two vectors at a point and you parallel transport those two vectors via the Levi-Civita connection, then the Riemannian inner product of that vector and its parallel transport is invariant. Okay. Okay. Right. So the affine connection could be chosen to be the Levi-Civita connection, for example. Which is metric compatible. In that the parallel transport pair of vectors has a Riemannian inner product that is constant. Okay, and then the other things, it's like which we had talked about, is this idea of the dual connections associated with divergence functions, right? We can also consider the affine connections induced by divergence functions, by divergences. Okay. All right. So, all right. So let me just actually let me just go ahead and stop here for now. It's like, and then the next thing we'll talk about are what I call tensors. It's like, so tensors are multi-indexed objects. It's like which transform in a particular way under the change of coordinates. Okay. So let me just stop here for now.